Okay, welcome everyone. I will go slowly at the beginning while I'm waiting for more people to arrive. I wanted to start by making some comments. Oh, let me make sure this video is wider. There we go. I want to start by making some comments on a homework problem, which I hope even those who are not turning it in looked at, and which those who are turning homework in enjoyed. The problem was to find and draw a finite set of circles on the Riemann sphere that's invariant under the action of the dodecahedral group. That is a copy of A5 contained in the automorphisms of the Riemann sphere. And let me just show you my own thoughts on this problem. So I like to use some kind of visual aid. So I have a little icosahedron here that I built with I think they're called polydrawn, these plastic equilateral triangles that you can fit together. And then I wrapped 6 rubber bands around it, as you can see. And those are the circles I propose to draw. So in thinking about this problem, one might notice that this group has order 60, and the traditional special points are like the center of a face of the dodecahedron. The pentagonal faces of the dodecahedron are 12 in number. So you might try to solve this problem by drawing the 12 circles, say tangent to one another, one for each face of the dodecahedron. But in fact, there is a circle that has an even bigger stabilizer than that one. That one has a Z mod 5 stabilizer. There's a circle whose stabilizer is of order 10. And it's just if you were to hold the icosahedron vertically, it's just the equator, which is this rubber band here. So the equator is not only stabilized under this order 5 rotation group, but it's also stabilized under a rotation that goes like this, which interchanges the north and south poles, i.e. the stabilizer is a dihedral group of order 10. So you can get away with 6 circles. And I won't go through all the details in the computation, but you can see in the screen I'm sharing what these 6 circles look like, both on the sphere and in the plane. And they turn out to have a remarkably simple description. Namely, so I'm thinking of, you take the equator and then you somehow find 5 more circles that are incident to it. So in the complex plane, you can take the equator to be S1, so let's call that C0. And then you're going to have 5 more circles, which are invariant under rotation by order 5. So once you find one of them, you're done. Well, it turns out that one of them is very easily described. Its center is at the point 2 on the real axis. And then since it's a great circle, it has to meet the equator in antipodal points, which means on the Riemann sphere, it has to meet the unit circle along the imaginary axis at 2 opposite points. So the circle of interest is just this one here. Of course, you can continue to draw it in the complex plane. And then when you take this circle plus its 5 rotates, you get the configuration that I've drawn here. And it looks a little funny because you might say, doesn't A5 involve all kinds of irrational numbers? There is one irrational number hidden here though, which is this distance is 1 and this distance is 2, so this distance is the square root of 5. So the field Q adjoint square root of 5 is necessary to draw this circle. And then of course you also need to be able to have the rotations, which enlarge the field a little bit more as well. Anyway, this is I think a very nice problem to show you that there's a little bit of depth to spherical geometry, and there's also some very elegant solutions to grappling with these interesting discrete subgroups. SU2 or SO3. Okay, so let's now go on to our main topic, which is hyperbolic geometry. And I want to describe 5 models or 5 ways of looking at hyperbolic geometry. So models for hyperbolic geometry. Hyperbolic geometry of the plane. So models for the hyperbolic plane. And the first one, which we discussed last time, was the upper half plane contained in the complex numbers with the metric, Euclidean metric divided by y, where c is x plus iy, y is the imaginary part of z. And let me just remind you that in this model, the geodesics consist of lines and circles that are perpendicular to the boundary. But there's, and if you were to take the parallel of a geodesic, it would also be a circle. But this is not a geodesic in its own right. In particular, it's not perpendicular to the boundary. But there's one other circular figure that's of great importance in hyperbolic geometry, which will be somehow the key really to understanding negative curvature, which is what's called a horocycle. So before I tell you what a horocycle is, let's ask ourselves, what does a sphere look like? By which I mean, of course, a circle of constant radius in H with respect to this metric. So I'm going to draw a circle with it. Let me put its center down here. Let's call this point will be actually fairly low, but I'll draw it as if it's high, epsilon I. So the center will be epsilon high, and it will pass through the point I. Now this hyperbolic circle, first it has to be, it's a round circle in the usual sense for the hyperbolic plane. So let me put epsilon I even lower. And so it will be symmetric about, in the hyperbolic sense, around the point epsilon I. In particular, it crosses the imaginary axis twice, once at I and once at another point that's the same distance from epsilon I as I is. So first, what's this distance from here to here? This distance, this is the radius of the circle, is the log of 1 over epsilon, as we get by integrating this metric along the imaginary axis. And there's a map of the hyperbolic plane to itself that sends this segment isometrically to this segment. What is that map? Its z goes to epsilon z. Remember, every element of SL2R gives an isometry of hyperbolic space. So the other place the circle passes through the imaginary axis is at epsilon squared I. So this is what a round circle looks like in hyperbolic space. In particular, its hyperbolic center is very different from its Euclidean center. And now, what happens as epsilon goes to 0? Well, obviously, the circle, this point on the circle just keeps getting lower and lower until it finally touches the real axis and is tangent to it there. So in the limit, a limit of these round circles is what's called a horoball. It's simply a circle tangent to the boundary of hyperbolic space and passing through some other point. This is a limit, this so-called horocycle is obtained as a limit of round circles. So this is very different from what happens in Euclidean space. Let's think about what happens in ordinary flat space. If you take a circle in flat space and you make it bigger and bigger, it converges to a straight line, which is a geodesic. But in negative curvature, a very large circle doesn't converge to a geodesic. This is not perpendicular to the boundary. In fact, this has geodesic curvature equal to 1, this shape. this is what's called a horocycle, and you can think of it as a circle centered at infinity. Morally, this point where the horocycle touches the boundary of the upper half plane is its center because it's the limit of the centers of these finite balls. Okay, so I just wanted to bring in this additional element of hyperbolic geometry. Besides geodesics and circles, we also have horocycles, and these will play a big role in what's to come. Okay, so another way to look at hyperbolic space, which makes the circles easier to visualize, is the disk model. So we take the unit disk, the set of points of absolute value less than 1 in the complex plane. And here the metric becomes 2dz over 1 plus the absolute value, 1 minus the absolute value of z squared. And this model is really the same as the hyperbolic space model. There's a Mobius transformation that sends the upper half plane to the unit disk, say z minus I over z plus I. That sends I to 0, and it sends minus I to infinity. It sends the real axis to the unit circle. And since Mobius transformations preserve circles in this model, which is called the Poincare disk model, the geodesics are, again, just circles perpendicular to the boundary. The horocycles are circles tangent to the boundary, since angles and circles are preserved. But what's nice to visualize in this one is that if you look at the origin, then the balls around the origin, the circles that we were constructing previously around I, are just ordinary circles in the complex plane by symmetry. And indeed, rotation around the origin is part of the group of isometries at this space. Okay, now in the first model, the isometry group was equal to SL2R. Of course, this is really preserving orientation, and this is technically modulo plus or minus the identity. What is the isometry group of the unit disk? Well, remember, this was actually the same as the automorphism group of the upper half plane. It's just as conformal maps of the upper half plane to itself happen to all be isometries. Same here, the isometry group of the unit disk in the hyperbolic metric is equal to the automorphism group of the disk. So it is, again, a group of Mobius transformations. Which ones are they? Well, they turn out to be the ones that look like this. They're A, B, B bar, A bar, such that the absolute value of A squared minus B squared equals 1. Thought of as sitting inside of SL2C, which is the group of Mobius transformations. And of course, we're always remembering to mod out by plus or minus the identity. The minus the identity acts trivially as a Mobius transformation, although it's non-trivial as a matrix. Now this set of matrices should look familiar. It looks a little bit like what we got for the sphere. What we got for the sphere also had some complex conjugations in it. So if you wanted to verify this, one way would be to just take SL2R, conjugate it by this matrix, and see that you get matrices of this form. But there's a more perspicacious way to say why this is the isometry group and to say what this group is. So when you see these B bars and A bars hanging around, it should make you think of Hermitian metrics. So there should be some sort of Hermitian metric that's preserved by this group of matrices. And in fact, the Hermitian metrics that's preserved, there's a hint about it right here. Because if this is a Hermitian matrix, then each of its rows should be unit vectors for that Hermitian metric. So this is, in fact, the orthogonal group or the unitary group of a Hermitian metric, but not the standard one, the one of signature 1, 1. So this group is isomorphic to SU 1, 1. In other words, we can think of it as acting on C2 and preserving the inner product on C2, which is of the form ZW. This is an inner product on C2, a Hermitian form, which is of the form Z1 W1 bar minus Z2 W2 bar. And there's a big difference between the Hermitian metric of signature 2 and the Hermitian metric of signature 1, 1. The difference is there are some vectors here whose length is 0. Namely, if A and B are the same. But remember the relationship between the action of this on hyperbolic space, on the disk and on the plane, and its action on C2 is via projective coordinates. So if we think of a point, you see what we have is a map of C2 to CP1, which we think of as the Riemann sphere. And here we have an action of SL2C. And here we have its same action by Mobius transformations. And this action is equivariant. We change our coordinate here to be Z2 over Z1 if we choose coordinates Z1 and Z2 on C2. And then what we see here is that the within C2, with respect to this inner product, we have two different kinds of lines. We have positive lines, negative lines, and null lines. A null line is a line where all the vectors have modulus 0. So have norm 0. So what's a null line? A null line is where ZZ is equal to 0, but ZZ is Z1 squared minus Z2 squared. So the lines with length through the null vectors correspond to points on the Riemann sphere where Z1 and Z2 have the same absolute value, which means that the absolute value of Z is equal to 1. So in fact, the unit circle corresponds to the vectors Z1, Z2, such that the norm, or let me just call it Z squared, that's too strange looking, Z dot Z is equal to 0. And indeed, the unit disk itself corresponds to the positive vectors. That is the vector such that Z dot Z is positive, and the outside corresponds to the negative vectors. Okay, so again, there's a close relationship between hyperbolic geometry and linear algebra in the same way as there was for the Riemann sphere. Let me make one other comment of a more sophisticated type about this stuff. Where do you first learn about the upper half plane in complex analysis? Well, one of the places is in the study of elliptic functions. So secretly, the upper half plane is a way of describing all of the lattices in the complex plane. So H corresponds to lattices in C. In fact, lattices with a choice of basis. And concretely, if you have an element tau in the upper half plane, you can make it correspond to the lattice Z plus tau Z. And then you get into the discussion of doubly periodic functions, the action of SL2Z, and so on, which we will come back to. But I just want to remind you that the upper half plane has something to do at the end of the day with complex tori, because you can then associate to this lattice the Riemann surface X, which is the complex plane modulo Z plus tau Z. And so Riemann surfaces of genus 1 are naturally parameterized by points in the upper half plane. There, the moduli space of such is parameterized. But the upper half plane is isomorphic to the unit disk. So does the unit disk also somehow, in some natural way, parameterize the complex tori? And it does. And the nicest way to think about this, or the most natural perhaps, is via Hodge theory. So there's a relation of this to Hodge theory, which goes as follows. If you take a topological surface of genus 1, then the first cohomology of this surface with coefficients in C, well, of course, it's isomorphic to C2. There's two standard generators of homology coming from these two loops, and their duals give generators of cohomology. But when this has the structure of a Riemann surface, this space splits as H10 plus H01. That is, there's the span of the holomorphic 1 forms and the span of the anti-holomorphic forms. And by Hodge theory, they represent all of the de Rham cohomology of this Riemann surface. And now before you end up put in this complex structure, here on this topological surface, we have an inner product. There's the symplectic form, which tells you the intersection number between two elements of homology. Or, if you like, on the level of de Rham cohomology, put that in here, you have an intersection pairing between two smooth 1 forms on this surface, which is given by I over 2 times the integral of alpha with beta bar. In other words, topologically, the complex cohomology of a torus carries a natural Hermitian form. And what does the signature of this form turn out to be? It turns out to be 1, 1. So in fact, the symmetry group SU11 can be related to the symmetries of this surface that preserve the intersection pairing. And then what is this Hodge structure here? This turns out to be enough information to uniquely determine a complex torus. And what it corresponds to is taking this space, which has this inner product of signature 1, 1, and splitting it into two subspaces, one of which has signature 1, 0, and the other of which has signature 0, 1. And each of these spaces are one-dimensional. And moreover, there's a natural requirement, which is that H10 is equal to H01 bar. The holomorphic and anti-holomorphic forms are conjugates of one another. And so what we see is that the complex structures on a surface of genus 1 correspond to the positive lines in this natural space of signature 1, 1. So complex structures on sigma 1, in other words, the number of ways of making this into a Riemann surface correspond to, via Hodge theory, the positive lines in H1 sigma C, which is itself isomorphic to what I'll call C11. It's a two-dimensional complex vector space with a Hermitian form of signature 1, 1. And we've just seen that the positive lines correspond to the unit disk contained in the complex plane.
Kurt?
Yes.
Just to be clear, so when you say positive line, you mean like the locus of vectors that have positive self-pairing?
No. So a positive line is a vector of the form C dot V. That's what a line is. V is a vector in C2. And it's a positive line just if V is positive. Okay, so the vectors that, the way C2 looks, grosso modo, is something like this. There's the null vectors, where V dot V is equal to 0, and then there's the positive vectors, and then there's the negative vectors. And the positive vectors, when you pass the projective space, give you the unit disk. So the choice of a point in the unit disk is the same as the choice of a positive line in this two-dimensional vector space. Since what we do is we think of the Riemann sphere itself as being the projectivization of this C2 here. Other questions? Okay, so that was a little glimpse of the disk model. One little remark I'd like to make about this, which is just a nice cultural aside, for those of you who have studied complex analysis or conformal mappings. One thing you'll notice about, well, let me say this. If we have a region U contained in the complex plane, there's a nice metric we can put on this region called the 1/d metric. So the 1/d metric on this region is given by the Euclidean metric divided by the distance from Z to the boundary of U. So the idea of this metric is you try to make the region U more complete. So this figure has unit size, but then when you're close to the boundary, you scale by 1/the distance. So this figure here, which you might not be able to see, but it's a scaled down version of this, it has the same size. As you get closer to the boundary, if you scale by 1/the distance, then lengths remain the same. And one thing you'll notice is that the 1/d metric is exactly, on the hyperbolic plane, is exactly the hyperbolic metric. So the rho on the hyperbolic plane is equal to the 1/d metric on the hyperbolic plane because y is the distance of Z from the boundary of the upper half plane. This distance being in the Euclidean sense. So we have a region in C. We want to take the Euclidean metric and modify it to make it look more hyperbolic, so we divide by the distance from the boundary. Now what about this metric here on the unit disk? 1 minus Z squared is not the distance to the boundary. The distance to the boundary is 1 minus the absolute value of Z. But notice that that we can factor the denominator. So this is 2ZZ over 1 minus the absolute value of Z times 1 plus the absolute value of Z. And as you go to the boundary of the disk, as the absolute value of Z goes to 1, this term goes to 2, and this term is equal to the distance from Z from the boundary of the disk. And so this 2 cancels with this 2, and what we find is that the hyperbolic metric on the unit disk is in fact asymptotic to the 1/d metric on the unit disk. So in both cases, the 1/d metric is actually a pretty good approximation to the hyperbolic metric. And when you're trying to visualize the hyperbolic metric, it's a lot easier to just think in terms of the 1/d metric. And if you do, well, you're only going to be off by a bounded factor. So let me just mention the following theorem. If U is a simply connected region in the complex plane, and it's not the whole plane, then there is an isomorphism by the Riemann mapping theorem to the unit disk. And this isomorphism is well defined up to composition with an automorphism of the disk. But the automorphisms preserve the hyperbolic metric on the disk. So we can take the hyperbolic metric on the disk, pull it back to this simply connected region, and get a canonical hyperbolic metric on U. This is just an instance of the fact that any Riemann surface whose universal cover is hyperbolic space carries a canonical hyperbolic metric. So in particular, every plane region carries a canonical complete hyperbolic metric of constant curvature -1. So you might wonder, if I'm looking at a plane region, can I figure out what rho of U is? And the answer is no, usually, because you'd have to be able to compute the Riemann mapping explicitly. Like for this wobbly region, it would be very hard to compute that mapping. Nevertheless, one knows approximately what this metric is to within a bounded error, and it's nothing more than the 1/d metric. So let me just mention this as a theorem, which is a simple consequence of the Schwarz lemma and something called the Kubba 1/4 theorem, which is that on any simply connected region U contained in the complex plane, other than the complex plane itself, which has no hyperbolic metric, the hyperbolic metric on U is bounded above and below by the 1/d metric. And the factors, in fact, it's within a factor of 2 in either direction of being the 1/d metric. Okay, so that's a good way to think about the approximate behavior of these two metrics and indeed of the hyperbolic metric on any plane region. Okay, so now we come to our third model for hyperbolic space. And well, one way to think about this is we're going to now draw hyperbolic space as a sphere. So remember that perhaps the simplest approach to spherical geometry is to just draw a sphere in three-dimensional space and say, take the induced metric. But here, I didn't draw the hyperbolic plane in an ambient space. I just said, here it is as a surface, here it's its metric, similarly for 2. Now I'm going to describe hyperbolic space as a sphere in a larger space. And you might say, well, that makes no sense. There's only one sphere. And that would be true. In any given Euclidean space, there's only one sphere. So what we're going to do is not work in Euclidean space, but in just a mild variant of it. And as you can guess from everything that's coming along, that the mild variant of it is obtained by changing the signature of the inner product on Euclidean space. So this third model is called the Minkowski model. And we will work in a space I call R21 with coordinates x, y, and t, and with an inner product which makes the inner product of a point with itself, that is the corresponding quadratic form, will be x squared plus y squared minus t squared. And often, for brevity, I'll just write this as p squared. Okay, so the Minkowski model deserves to be treated on an equal footing with good old R30, which is where the ordinary sphere took residence. That's one reason why Minkowski space is important. Why is this important from the perspective of physics?
Is this spacetime?
Yeah, that's right. So that's why I chose T here. It's very natural to think of Minkowski space as space-time. So if you have 2 points that lie in a plane where T is constant, in other words, you have a slice of a space-like slice of Minkowski space, then the length of a vector is just its ordinary spatial length, which comes out to be positive. But if you have a vector which points like the path of a light ray, it'll turn out that its length is 0. Actually, technically, if I wanted to do general relativity, I put a c squared in front of there, where c is the speed of light. So if you like, this is c equals 1 special relativity. And of course, it's not quite special relativity of the universe we live in. It's special relativity in a world of 2 space dimensions, not 3. So there's 2 space dimensions, 1 time dimension. And then, in addition to vectors which point in a space-like direction, there are vectors that travel at the speed of light, and then there are vectors that travel faster than the speed of light. And they have negative length in this metric. And what we're going to do is take the space of vectors that go faster than the speed of light and turn it into hyperbolic space. So hyperbolic space in this model will be the set of P such that P squared is equal to -1. The fact that this is negative means they correspond to vectors going faster than the speed of light. And well, let me draw you what this space looks like a little bit. So To say p squared is equal to -1 is the same thing as to say x squared plus y squared is equal to t squared minus 1. So of course this has no solutions once t is between plus or minus 1. T has to be larger than 1 before this begins to have solutions. And then you get the solutions are circles for any fixed value of t. And so what this locus looks like in R21 is a hyperboloid in the region where t is bigger than 1, and another hyperboloid in the region where t is less than 1, and then there's nothing in between. So this is x, y, and t here. And since this space is disconnected, to have a good model for hyperbolic space, I'm going to just take one component of it. So I intersect this with the locus where t is greater than 0. And morally, this is a sphere because the length of the vectors is constant, and this is its radius squared. So this is sometimes called the sphere of imaginary radius. Okay, so now that's my model for hyperbolic space. What is the metric I'm going to put on this space? Well, the metric will be the induced metric. In other words, here we have a metric on R3 or R21. It happens to have indefinite signature. It's a Lorentz metric. But it turns out that when we restrict it to the hyperbolic plane, when we restrict it to these tangent spaces, then it turns out to be positive definite. For example, if I were to take the tangent plane at the lowest point in hyperbolic space, then the tangent vectors would point in the x and y directions exclusively. There would be no vertical component. And so the restriction of the inner product to those tangent vectors is positive definite. That's actually because this line here, the line to p, it has a negative definite inner product on it because p squared is -1. The whole signature overall is 2, 1. So if you just decompose the space as p and p perp being this tangent space, p has signature 0, 1, and p perp has signature 2, 0. Now it's an easy fact, just as in the case of SO3, in the case of the ordinary two-sphere, that SO21, that is the orthogonal group for this inner product, acts transitively on H. And I'd like to say that it preserves H as well. You would think that the orthogonal group would preserve the sphere of a given radius, but it doesn't quite because I chose H to be just one of the two components here. And there are elements of SO21 that swap these two components. But if I restrict to the connected component of this group containing the identity, then it can't possibly swap the two components. And so then it acts on H, and it does so transitively. So this means connected component of the identity. So in general, when one is discussing the relationship between linear groups and groups of isometry, there are these small nuances of sort of plus or minus 1. There's plus or minus the identity for SL2R. There's whether or not you take the connected component here, etc. And I'll tend to sweep these things under the rug. I'll say slightly incorrectly, the symmetry group in the Minkowski model, the isometry group is SO21. Slightly wrong. When it really needs to pass to this subgroup of index 2. Wow, okay, so this is a very different looking model for hyperbolic space, but it should look somewhat similar to the sphere. So for example, let's figure out what a geodesic looks like. So there should be a geodesic which sits in the x plane, xt plane, and travels at unit speed through this point 0, 0. So what might this geodesic look like? Well, on the ordinary sphere, that geodesic was parameterized by sine and cosine. In this case, it spanned, as you might guess, by hyperbolic sine and hyperbolic cosine. So a typical geodesic, let me write it up here. So an example of a geodesic is gamma of S is the x-coordinate has to start, we want the x-coordinate to start at 0, so it will be the sinh of S. But then the t-coordinate has to start at 1, so that will be the cosh of S. And then I claim that the two of these put together parameterize an arc along the sphere of radius of imaginary radius, and moreover, they do so at unit speed. So first, let's see make sure we're on h. So what's the length of this vector? Well, it's sinh squared minus cosh squared. And cosh minus sinh is 1, so sinh minus cosh is minus 1. So indeed, this is a path that stays on the hyperboloid. And what about its speed? So gamma prime of S is, when we differentiate, sinh becomes cosh becomes sinh, and we get that the norm of the derivative is cosh squared minus sinh squared. We just reverse these two terms, which is plus 1. So this is a typical example of a geodesic. Now there's another way to think about this geodesic, which is just that it's the intersection of this upper half plane, this hyperboloid, with the plane defined by the equation that, that y is equal to 0. So when you cut the hyperboloid by a plane through the origin, what you get in this case is a geodesic. But the orthogonal group preserves planes. So in fact, whenever you cut this hyperboloid by a plane through the origin, if you get something, what you get is a geodesic. So in general, we can say that in this model, the geodesics correspond to planes. The geodesics correspond to planes that meet H via gamma equals H intersect that plane. By the plane, I mean a plane through the origin, a subspace of R21. Now, how do you describe a subspace in an inner product space? The nicest way to do it is to just take its normal. So when I want to describe this plane here, or let's say to make it more visually appealing, this plane here, to describe this plane, it's enough to give its normal vector, q. Then I can call the plane q perp. So for example, y equals 0 is just the same thing as 0, 1, 0 perp. And because of the fact that we want planes that cross the hyperbolic plane, it turns out we're only interested in the cases where q squared is positive. And if q squared is positive, then we can normalize it so by a real scalar so that q squared is equal to 1. So in addition to the sphere of imaginary radius, there's also the sphere of radius 1 in this picture. Let me erase some of the distracting material here. In fact, let me start all over again. So a second element of the Minkowski model is what's called the one-sheeted hyperboloid. So H was described by p squared equals minus 1. There's another hyperboloid described by p squared equals plus 1. And if we take a point on this hyperboloid, and then we take its perp will be some kind of a plane. P perp. I'm drawing it as a line, but it should really be a two-dimensional plane, and it will cut the one-sheeted hyperboloid in a geodesic. In fact, there are two vectors which could serve as a perpendicular to this plane. And if we choose an orientation for R3, we can then use the choice of this vector versus this one to give an orientation to this geodesic. So that if we replace P by minus P, we get the same geodesic with a reversed orientation. So it's nice to call the one-sheeted hyperboloid curly G because its points correspond to geodesics. And then if we put oriented geodesics here, then the oriented geodesics are in bijection with the points of G, which is the set where P squared is equal to +1. Well, there's one more salient feature here which cries out to be described, especially if you're a physicist, namely the light cone. So if you're going to have vectors that are positive and negative in length, then you're also going to have vectors that are 0 in length. And this space, which I'll call curly L for light cone, this is the locus where P squared is equal to 0. And it turns out that the points on the light cone correspond to horocycles. So these will correspond to horocycles. And I think I'll defer the explanation of how these correspond to horocycles later. Yeah, let me do that. I can say very quickly what you do. If you're given a point on the light cone, then you associate to it the locus of, so from V, you've got the horocycle HV, which is the set of P such that P dot V is equal to 1. And that turns out that's a plane that does not go through the origin. It's an affine plane, and it cuts the hyperbolic plane in some sort of figure that looks like this. But more to the point, what do the points of the light cone correspond to? They give a way of forming a boundary for the hyperboloid. As you move off along the hyperboloid, the corresponding vector gets closer and closer to a vector in the light cone. So the hyperboloid, it seems, can be compactified by rays in the light cone. And that's true, but it's not true in this picture because there's no obvious way to attach the two. And that brings us to the fourth model. Okay, so the fourth model is called the Klein model. And what we do here is we pass to the projective space of Minkowski space. So after all, if I want to specify a point in the upper half on this hyperboloid, it's enough to specify the line that goes through that point, since that line meets the hyperboloid in only one point. So if I pass to projective space, there's an injective map of H into projective space. And in fact, we can do this in such a way that the point, say x, y, t, in R21 corresponds to the point, let's call it with homogeneous coordinates, x over t, y over t, comma 1. Or just the point x over t, y over t in a copy of the affine space R2. This is isomorphic to RP2, and the locus where t is not 0 gives you an affine slice contained in this real projective plane. Okay, and now what we notice is that, in fact, the hyperbolic plane lies in the region where t, it's not only is it not 0, but it's bigger than or equal to 1. So what do the points in H correspond to? Well, remember, for H, to be in H, you have to have the property that x squared plus y squared minus t squared is equal to -1. So let me write that differently. X squared plus y squared is equal to t squared plus 1. And so if we divide through by t, we see this corresponds to x over t squared plus y over t squared is equal to 1 plus 1 over t squared. So what points in R2 can be written in this form? Well, they can be written in this form as long as this coordinate plus this coordinate squared is, I wanted the sphere of -1. T squared minus 1, 1 minus t squared. This is less than or equal to 1. So what we find is that the hyperbolic plane just corresponds to the locus in R2 where these two coordinates are less than 1. 1 minus t squared is always less than 1. So the hyperbolic plane corresponds to the ball consisting of xy, x squared plus y squared are strictly less than 1, contained in RP2. Okay, so sorry, that was slightly confusing because there's two x's and y's going on. Let me just draw the picture. So you just have to take this picture in RP3, in R21 rather, and take the corresponding picture in projective space. And what happens is the light cone, which is defined by the homogeneous equation, x squared plus y squared equals t squared, goes over in affine coordinates to just the unit circle. X squared plus y squared is equal to 1. I.e. in RP2, you pass from homogeneous to inhomogeneous coordinates by just setting t equal to 1. And then the hyperbolic space itself corresponds to the ball bounded by this light cone. And now, what are the geodesics? So the geodesics here corresponded to planes, meaning the ball. So the geodesics here, when you projectivize a plane, you just get a straight line. So the geodesics now have become straight lines. And so we have a very beautiful and simple model for hyperbolic geometry. The space is the unit ball. The lines the geodesics are straight lines. And the symmetry group is maybe not quite so obvious, but it's basically SO21, which sits inside of GL3R, which is equal to the automorphisms of RP2. So basically what you get is the automorphisms of RP2, which preserve this conic. So indeed, there's a close relationship between hyperbolic geometry and projective geometry via this Klein model. By the way, if you were trying to disprove that the Euclid's fifth postulate is independent, again, all you have to do is come up with a model for some sort of geometry which satisfies Euclid's postulates but doesn't satisfy the parallel postulate. And what happens here in traditional Euclidean geometry, the parallel of a line is just another line that doesn't meet it. And there should be a unique parallel through a given point. But you can see here, there are many parallels to this line through a given point. So Euclid's fifth postulate is violated. Now, what's wrong with this model? Why doesn't everybody just use this model and forget the stupid Poincare model? Well, one reason is angles are completely wrong here. There is a notion in hyperbolic space, as in any Riemannian surface, of the angle between two vectors. And the angle that you see here in the Euclidean plane is very far from being the actual angle. The Poincare model is conformally accurate, which is why it maybe is closer to carrying the geometric content of hyperbolic space. Okay, and now there's one more model I want to mention. And it might not even sound like a model, but in fact, it opens the doorway to the connection between the geodesic flow and other dynamical features of hyperbolic surfaces and the analysis of homogeneous spaces for Lie groups. So it's very simple. I call it the homogeneous model, the homogeneous space model. So let's go back to our first model. We have the hyperbolic plane, we have this metric, and we have its isometry group. So we let G be equal to the isometry group, which is SL2R mod plus or minus the identity. Or more intrinsically, we think of G as being the isometry group of the upper half plane. And now, within this group, there are lots of compact subgroups, namely the stabilizer of a point. If you have a point in hyperbolic space, its stabilizer in the isometry group is just rotations around that point. In particular, sitting inside of K, of G, is K, which is SO2R, modulo plus or minus the identity. In fact, it's a famous theorem, and this is a nice exercise, that SL2R retracts onto SO2R. Every Lie group retracts onto a compact subgroup. If you wanted to compute the fundamental group of SL2R, it's just the same as the fundamental group of this compact subgroup. It's a circle. And this group is nothing more than the stabilizer of the point C equals I in the upper half plane. So if you were to write this group out explicitly, its elements would be of the form cosine theta, sine theta, minus sine theta, cosine theta. And you would find that they correspond exactly to the Mobius transformations that fix the point I. But G acts transitively on H. And so, as is always the case, when you have a transitive group action, there's a natural bijection between the orbits of that group and the group modulo the stabilizer of one point. So we can write H as equal to G mod K. And how do we obtain a correspondence here? What we do is we send G to G of I. And you see, if we were to replace G by G times K, where K is in this compact group here, K fixes I, so G of Ki is the same as G of I, because K of I is I. So we get a bijection between the upper half plane and this particular quotient of the group G. And this perspective opens the door to many different ways of looking at hyperbolic spaces. In particular, it suggests that we're kind of prejudiced about dealing with spaces that have positive definite Riemannian metrics. We like that because we're familiar with geometry and length, and we have a good intuition for that. But it suggests that in addition to studying hyperbolic space, we should also study G mod H for other closed subgroups of G. And these might not carry Riemannian metrics. When you take a quotient by a compact group, it always gives a Riemannian manifold. And these other homogeneous spaces will turn out to play a central role in the study of hyperbolic space itself. Okay. So, so two remarks before we go on to studying quotients of hyperbolic space. Our main topic of interest will not be just hyperbolic space itself, but hyperbolic surfaces, those that are modeled on hyperbolic space, surfaces of genus 2, for example. But before I go on to that, there's a good set of 5 choose 2 equals 10 problems to work out here, which is you should be able to find a nice way to go between any two of these models. You should find there's some relatively natural way to transport yourself from the Minkowski model to the Klein model to the homogeneous space model to any pair, between any pair. So for example, I've already told you how to go between these two pairs by a Mobius transformation. So let me just say one of the ways of connecting these various models. I think the strangest connection is between the Klein model, where geodesics are straight lines, and the disk model, where the geodesics are circles. And what's strange about this is that in both cases, the space is the unit disk. How can there be two versions of hyperbolic geometry on the unit disk? So let me tell you how to visualize this. So one way is we start with the Poincare model. So this is model 2, and our geodesics are round circles. And we're sitting in the complex plane. And now, since we're experts in spherical geometry, we know how to turn the complex plane into a copy of the round sphere sitting in R3. And this transformation is again conformal. So now these geodesics perpendicular to the boundary, these go to circles perpendicular to the equator on the Riemann sphere. And that's nice because notice that a geodesic that's perpendicular to the equator is just the intersection of the southern hemisphere. This is now the southern hemisphere here. This was the original unit disk. It's the intersection of the southern hemisphere with a vertical plane. And now what you do is you just look at this from above. Or, if you like, you project it to the plane. Project it orthogonally to the vertical axis. In other words, just take the x and y coordinates. And when you project to the plane, the projection of the southern hemisphere is again a round disk. But now each of these lines, because you're projecting in the vertical direction, each of these semicircles projects to a straight line. And that's the connection between the Klein model and the Poincare model. There's one other connection I want to mention, and we'll come to this when we do some specific constructions, which is that you'll remember that we actually had names for all the different kinds of vectors in Minkowski space. So in RP21, the inside of the ball corresponds to hyperbolic space. The boundary of the ball corresponds to the light cone. So we see now how the boundary of hyperbolic space is naturally compactified by the light cone, because it's just the closure of the open unit ball. But there's more going on, namely the outside of hyperbolic space is the projectivization of G, the one-sheeted hyperboloid, or the space of geodesics. So there should be a way to canonically attach a geodesic to every point in the outside of the hyperbolic ball. And the construction of this is extremely beautiful. What you do is if you have a point Q out here, then you draw the two tangent lines to the circle that you see from Q, and then you connect them by a straight line. And this line represents Q perp. It's the geodesic corresponding to that point Q. And now here's one of the really neat features. When you go from the complex plane to the Riemann sphere, to this S2, that maps an isometry on the equator. And when you map back down to the unit ball, it's again an isometry. So going from here to here to here doesn't change the circle at infinity. The boundary of the unit disk in the Poincare model is canonically identified pointwise with the boundary in the Klein model. So if you have a point outside of the unit disk in the complex plane, it also determines a Poincare geodesic. And which Poincare geodesic is it? Well, it's just the one that is orthogonal to the boundary, but passing through the same 2 points. So the corresponding geodesic in the Poincare model is, again, uniquely determined in a simple way by this point outside here. And moreover, this, these 2 lines here, since this is 90 degrees, these 2 lines are radii for that circle. So the corresponding Poincare circle looks like this. And if we were in the Poincare model, you would then get some sort of, you could then construct a right triangle going like this, this, and this. And what you find using that right triangle is the following beautiful fact. If Q corresponds to the point x, y, t with x squared plus y squared minus t squared equal +1, then the center of the circle, C, is what you get by projectivizing this. And so the center is x over t, y over t. And then the radius of the circle turns out to be 1 over t. So when you compute the center of a circle using the Minkowski model, it very quickly translates into a description of the corresponding circular arc in the Poincare model. And the fact that this is 1 over t comes from the fact, again, that if you divide this equation by t squared, you'll be able to solve this, this right triangle here where this side is 1. In fact, what you get is that the radius of this triangle, running out of space here, the radius squared is x over t squared plus y over t squared. And that's the hypotenuse of this triangle. And that should be equal to 1 plus this length here. And indeed, that's 1 plus 1 over t squared. Because if we multiply through and clear denominators, that just becomes this equation here. Okay. So that's one remark about these models. It's very helpful in terms of visualizing hyperbolic space to try to imagine how you go between them. Another remark, which I'm not going to belabor at this point, but which is really has to be mentioned, is that there are such things as hyperbolic n-manifolds. Hyperbolic geometry is not limited to dimension 2 any more than spherical geometry is. So if we wanted to do n-dimensional hyperbolic space, well, in fact, everything that I've said so far goes through. And perhaps the main thing to say is that first, you would deal with the group SON1 instead of the group SO21. And then you would have the Minkowski model, the Klein model, etc. There are also Poincare models and upper half-space models. That works in general. And the second thing I want to mention is that in the case of hyperbolic 3 space, the boundary of hyperbolic 3 space, which is a 2-sphere, just as it's a circle in the case of dimension 2, can be naturally identified with the Riemann sphere. And what happens is that the isometric geometry of H3 becomes conformal geometry at infinity, and the isometries of H3 act by conformal transformations on the Riemann sphere. Moreover, every conformal transformation is realized, and the only isometry that acts by the identity on the sphere is the identity. So indeed, the isometries of hyperbolic 3 space correspond naturally to the full group of Mobius transformations, SL2C, modulo plus or minus the identity. So somehow one could imagine, in fact, that, let me just say, make this point, what do planes correspond to in hyperbolic 3 space? In the ball model, they correspond to, again, not circles, but spheres that are perpendicular to the boundary. So in the ball model, the hyperbolic planes in H3 look like this. In the upper half space model, they look like this. They're hemispheres, or they might consist of a vertical plane, just as a line is a geodesic in the upper half plane. And their traces on the sphere at infinity are circles. So the well-known fact that Mobius transformations send circles to circles is just a manifestation of the fact that the isometries of hyperbolic 3 space preserve hyperbolic planes. They send planes to planes. Okay, so that's just a glimpse of higher dimensions. Okay, so our next goal is to start constructing some examples of hyperbolic manifolds. So we want to construct explicitly some hyperbolic manifolds like X is equal to gamma modulo H, where gamma is contained in the isometries of hyperbolic 3 space. For example, it turns out that any Riemann surface of genus 2 can be realized as a quotient of the hyperbolic plane. So we'd be interested in constructing groups of isometries of hyperbolic 3 space, or perhaps we'll find other mechanisms for constructing hyperbolic surfaces. And then our goal will be to study the geodesic and horocycle flows on these hyperbolic surfaces. That's the sort of the next level of ergodic theory beyond the sort of compact abelian groups that we've been studying to date. So to do that, we're going to need a little trigonometry. Or it's useful to know a little trigonometry, just as we had for in the case of the sphere. And in particular, it would be nice to have an interpretation of the inner product between 2 points in Minkowski space. What does the inner product between 2 vectors in R21 mean? Well, it should come as no surprise that the inner product between 2 vectors in the upper half plane has something to do with their distance, because as we saw in the case of the sphere, the inner product between 2 points literally gave the cosine of their distance measured as an angle. And it's easy to guess what this inner product should be by considering the geodesic we drew before, which was sinh s 0 cosh s. So if we call that gamma s, then we know that the distance from gamma 0 to gamma s is s. But what's the inner product? The inner product between gamma 0 and gamma s, the Minkowski inner product, that's the inner product with 0, 0, 1. That's this first vector here, 0, 0, 1. The inner product just has one term, and it's this term here, which is the minus the cosh of s, which is the distance between them. So what we find is that if P and Q are in hyperbolic space, then the inner product between P and Q is minus the cosh of the distance from P to Q. Okay, so that gives a convenient way to concretely measure distances if you can figure out what their coordinates are in the Minkowski model. But now there's another interesting question that begs to be answered, which is, what if we take 2 geodesics That is, what if we take 2 points on the light cone, P and Q out here, on the one-sheeted hyperboloid, I mean, 2 points on this locus G, and we take their inner product? What is that going to measure? And it's interesting, there's 2 things it could measure. So first, those correspond to oriented geodesics in the hyperbolic plane. So if this is P perp and this is Q perp, thought of as geodesics, there's an obvious angle here, alpha, between them. So maybe the inner product has something to do with their angle. And we saw in the case of the sphere, in fact, the cosine of that angle was basically the inner product. But in hyperbolic space, there's another possibility, which is that the 2 geodesics might not cross one another at all. And in that case, they have a different invariant, which is their distance. And so we get an inner product, which maybe in some cases should measure angle, and in other cases should measure distance. Also, points in this one-sheeted hyperboloid G don't just correspond to geodesics, they correspond to oriented geodesics. So the sign will change if we reverse the orientation, but the distance will not. So what do you think happens in the end? Well, let me just say, so if PQ are in G, then the inner product between P and Q can be 2 things. It's either plus or minus the cosine of the, well, actually, it's the cosine of the angle between gamma P and gamma Q, that is the corresponding geodesics. Or it's the cosh of the distance between gamma P and gamma Q. But with a plus or minus sign that's dictated by whether or not they're parallel or disoriented. So the cosh thing you could almost guess from what's happening here. The angle is very easily verified. You see, if you take a point on the unit circle, if you take a point with coordinates cosine theta, sine theta, 0, after all, that belongs to the one-sheeted hyperboloid. It just corresponds to a plane at angle theta. And as you change theta, that plane rotates. And the inner product between 2 vectors like this, say starting with 1, 0, 0, and then moving by angle theta, the inner product is just cosine theta. So this is almost obvious. And notice that you might think there's 2 angles that you could measure, but that's where we use the orientation. So you look at the angle you have to move P through until it coincides with Q. If you were to reverse the direction of Q, then you would measure this angle. And that would change the sign of the cosine. And the beautiful fact, which I will leave you to check, is that when you go past an inner product of size plus or minus 1, the cosh takes over for the cosine. So the cosine here ranges in minus 1, 1, and the cosh here with a plus or minus sign ranges in minus infinity 1, minus 1, and 1 plus infinity. Okay, so next time we will use trigonometry to construct some tessellations of the hyperbolic plane, analogous to this tessellation of the sphere. And then we will use those tessellations and perhaps some other considerations to give some concrete examples of hyperbolic surfaces. Okay.
Could you tilt the screen just slightly so the bottom focuses on, I don't know, like it's a bit blurry at the bottom.
Oh.
I just thought okay. It almost seems like having you in the frame made it focus a little bit better. So
sure.
Yeah, that's better actually.
Okay.
Okay, thank you.
The so-called screen is actually a tiny camera on a tripod, so I can tilt it, but I think it's parallel to the blackboard. Anyway, I can always stay out of the picture on request, so please feel free to ask. And I should say that everything I'm saying today is in the notes. So I think of the the lectures as a way of kind of rehydrating the notes and drawing a lot of pictures that are not present there, but in terms of what's written and the accurate formulas, they're all present in the write-up. So let me at least stop the recording.